Hello, we are group T4G and we worked on keyword spotting inference acceleration with HLS for this project. So what is keyword spotting? So keyword spotting using audio is a technique where given a dictionary, you identify every instance of each word in an audio file. So in the image below, you can see that someone might say, turn on the light and make it dark and green. And so you would provide some type of model, a dictionary, given keywords and phrases, just turn on, light, dark, and green. And um, you would then run the audio through your model and you would be able to identify every single word and where it was identified. And this is seen inside devices and technologies such as like Siri, Alexa, ad generation, and it's very up and coming, and it's going to be really integrated in Internet of Things. So how does it work? For our model, we ended up using 5 steps. So the first step is data collection and preprocessing. In this stage, you gather labeled audio data sets, and then you preprocess the audio into feature representations. From there, you then run the model and you train it. And you train an ML model to recognize keyword patterns that you provide given a dictionary. Then you do the inference stage. In this inference stage, you apply your trained model to new audio data for keyword detection. In the fourth stage, you do thresholding and decision making, where you set thresholds on model confidence scores, and then you are able to identify keywords based on thresholded scores. The fifth stage is post-processing and real-time operation, and this is a stage where you have to optimize how to do this real-time continuous audio processing. And if you see in the picture below, we have an input signal that says just the word yes. You then create a type of feature mapping for it, and you run it through your model. And once it passes through this neural network, then at the very end, you have all of these decision scores. So for yes, it'll be 0.91, no, 0.02, on, 0.01, off, 0.01. And then you can identify that because yes has the highest score, that's the input speech signal was yes.
There's a wide application of keyword spotting. It is always used in the wearable devices and IoT devices, and FPGA significantly help the implementation of keyword spotting in IoT device. So it all thanks to his features of parallel processing. It can execute operations concurrently, so it is good for energy saving, and we can also the customized hardware also improve system efficiency. Because in IoT device, there's limited CPU resource, so we can run all operations on FPGA and save CPU power for other operations. And there's a natural advantage of FPGA to accelerate some algorithm which includes a lot of convolutions and matrix multiplications. So it is good to use FPGA to speed up the process. So our input file is a 10-second audio file, and we will do the audio processing by reading the audio file and then sampling the data, applying the frame and window processing, and then it's FFT and filter bank and log map processing. And we will input our log map data into the neural network. After the neural network, we'll get our output result, which is we represent the possibility of each categories, and we select the maximum index.
Layers. The input pass through a depth-wise convolution layer. Subsequently, the output from the depth-wise convolution layer is processed through 4 DS block. Each DS block comprises both depth-wise and point-wise convolution. Within each DS block, following the DS block, the output undergoes a max pooling layer. Finally, the result of the max pooling is further processed through a point-wise convolution layer, which computes the final output. And our approach comprised the transformation of a MATLAB code into C++ for FPGA implementation. After identifying a suitable MATLAB code, we performed the necessary translation to make it compatible with FPGA execution. We focus on optimizing the utilization of hardware resource on the FPGA. Finally, to validate the accuracy of the computation, we compared the results obtained from the FPGA execution with those generated by running the original MATLAB code. The optimization process for matrix multiplication in our design involved the application of several key techniques. Initially, we implemented pipeline optimization on the loops responsible for matrix multiplication. The HLS report reveals a DSP resource utilization of 300% after applying pipelining, and it indicates that there's a resource overload. So we further optimized the design using loop tiling, a technique that partitions the pipeline loop into smaller chunks to conserve resource. And this strategy reduced DSP utilization to 87%, alleviating the resource burden observed during the initial pipeline phase. Additionally, we employed reshape by completely transforming the matrix along its second dimension. This reshaping aimed to expose parallelism, enhancing overall performance, particularly in a scenario involving frequent data access. The combined application of pipelining, loop tiling, and reshape techniques resulted in a more resource-efficient and high-performance matrix multiplication implementation.
So this is the result of our baseline design, running the baseline in the first layer, and this took around like 2.3 milliseconds. Because we had to do an intense matrix multiplication, it took a lot of resources, which made it difficult to run multiple layers without overutilize the total utilization of our resources. Our baseline design took about 2.36 milliseconds instead to run, and had a max latency of about 236,000 cycles used. Next slide. With the optimized version of our code, for the FPGA, we managed to reduce the total execution time by about 60%. However, there was a lot of overhead because, like, as you can see with the latency, there were about 3,700 or 3,800 cycles used for the entire process, but about 3,000 of those cycles were used for sending in data and sending in and out data through the input and output loops. And then only about 800 were used for the actual calculations. But through this, we showed a complete speed up of about 290 times the original design, and we only used 38 microseconds for this process.
So in our optimization design, we introduced the pipelining to improve the throughput, to have a better throughput. But this also introduced a lot of resource use because we need to run the calculations and data access, memory access in parallel. So it means that we have to consume more resource. So we will have a increase in the use of block RAM and also the DSP because we're doing the multiply accumulations in parallel. And also there's a lot more complex control logic, so we use more flip-flops. But we're also applying the array reshape, which help decrease the use of lookup table because it can rearrange the memory access, including the indexing patterns. So overall, it can have improvement in the lookup table use.
When evaluating the onboard latency, we saw for the baseline FPGA design, there was an average latency of 10.473 milliseconds with a standard deviation of around 2.6 milliseconds. And for the FPGA optimized design, we had 12.697 milliseconds with an average standard deviation of 5.573. And for the ECE software, we ended up getting around 25.25 milliseconds with a standard deviation of around 3.749 milliseconds. And as you can see, the difference between the baseline and the optimized average latencies aren't necessarily too large, but that is largely due to the fact that there is a lot of communication overhead that ends up providing around 10 seconds of, or that ends up providing around 10 milliseconds. And when you look back at the previous designs and the previous speedups, then the around 2 milliseconds of difference is accurately shown.
So let me introduce the result of our implementation. Okay, this is the output of our last layer. The maximum value has been selected as the result. And in this specific example, the decision is categorized as yes. So we can see that yes has the largest value, so it is selected as the final result.
So overall, we developed a functional keyword spotting inference accelerator, but we had some drawbacks of not being able to place the entire neural network on the FPGA. Our optimization had about 60 times overall improvement over our baseline version, which was a really significant achievement that we had. So the communication overhead from the DUT for data transfer eventually becomes like a bottleneck for that. So if we have more space in the FPGA, we could be able to put more of the neural network and speed up more of the process.
This is our code running on the FPGA.